Welcome, everyone. Today, we are diving into one of the most essential tools in biostatistics, the t-test. Imagine you are a scientist trying to figure out if a new fertilizer makes plants grow taller, or if a new drug actually lowers blood pressure. How do you know if your results are real or just a lucky coincidence? That is exactly what we will learn today. Let us get started. Now that we know what our goal is, let us look at how a t-test actually works. In any experiment, you will naturally see some variation in your data. A t-test acts like a mathematical detective. It looks at the size of the difference between your two groups and compares it to how much the data naturally varies in the background. If the difference is much larger than the background noise, the t-test tells us that our new fertilizer or medication genuinely worked. By the end of this lecture, you will perfectly understand the two main types of t-tests and exactly when to use each one. Building on that foundation, let us explore our first specific tool, the unpaired t-test. Suppose you want to test a new blood pressure medication. You give Group A the real drug and Group B a fake sugar pill. Because the people in Group A are completely different from those in Group B, their results are independent. The unpaired t-test is designed specifically for this exact situation. It compares apples to oranges, ensuring that the two groups have no connection to one another. It assumes your data forms a normal bell curve and that the natural spread, or variance, is roughly equal between both groups. Before we can calculate the final t-statistic, we need to understand the background noise in our data. This formula calculates the pooled standard deviation, represented by SP. It takes a weighted average of the variances from both groups, giving more weight to the group with more participants. The terms N1-1 and N2-1 are the degrees of freedom, representing our independent pieces of information. If the variance in either group increases, the overall pooled standard deviation increases. This means there is more background noise, which will ultimately make it harder to find a significant difference between your groups. Now that we have our formula, let us see this with a concrete example. Imagine a biologist testing a new protein diet on mice. We have 5 mice on a standard diet with a variance of 4, and 5 mice on the new diet with a variance of 6. We need to find the overall background noise. We plug our sample sizes and variances into the pooled standard deviation formula. The numerator simplifies to 16 plus 24, which is 40. We divide that by our total degrees of freedom, which is 8. The result is the square root of 5. This gives us approximately 2.236, which represents the average natural variation in weight gain across all the mice. With our background noise calculated, this brings us to the main unpaired t-test formula. The t-statistic is essentially a mathematical ratio. The top part of the fraction, x bar 1 minus x bar 2, represents the actual difference between the two group averages. The bottom part represents the natural background noise we just calculated, adjusted for the sample sizes. If the difference between the means increases, the top number gets bigger, and your t-value increases, indicating a stronger effect. Conversely, if the spread of the data increases, the bottom number gets bigger, shrinking the t-value, because the noise is drowning out the signal. Let us finish our mice example by plugging our numbers into this main formula. We know the standard diet mice gained an average of 10 grams, and the new diet mice gained 14 grams. We subtract 14 from 10 to get -4 in the numerator. In the denominator, we multiply our pooled standard deviation of 2.236 by the square root of 0.4. This gives us a final t-statistic of approximately negative 2.83. The negative sign just means the first group gained less weight. A value near 3 is quite large, meaning the difference is almost 3 times larger than the background noise. The biologist can confidently say the new diet works. To truly understand what we just calculated, let us look at this visually. Here you see 2 bell curves representing our 2 groups of mice. The blue curve on the left is the standard diet, centered at 10 grams. The green curve on the right is the new diet, centered at 14 grams. The distance between the peaks is the signal, or the difference between the means. The width of the curves represents the variance, or the noise. Because the peaks are pulled far enough apart relative to how wide the curves are, our t-test confirmed that these 2 groups are genuinely different, not just overlapping by random chance. Now that we have mastered independent groups, let us imagine a completely different scenario. Suppose you want to know if a workout program helps people lose weight. Instead of 2 separate groups, you weigh the exact same people before the program and then again after. Because you are measuring the same individuals twice, the data points are deeply connected. This is where the paired t-test comes in. Instead of comparing overall group averages, it looks at the differences within each specific pair. By focusing only on how each individual changed, the paired t-test brilliantly eliminates the natural variation between different people. You might wonder why we need a separate test for this. The paired t-test is incredibly powerful because it is highly sensitive to small changes. In medical research, people naturally have vastly different baseline health metrics. If we used an unpaired test, natural differences like genetics or starting weight might completely hide the actual effect of the treatment. By pairing the data, each person acts as their own control group. This drastically reduces the background noise, making it much easier to detect if a drug or training program actually works. It is the ultimate statistical tool for any before and after study. This brings us to the elegant formula for the paired t-test. Conceptually, it is much simpler than the unpaired version because we have condensed 2 sets of data into a single set of changes. The numerator, d bar, is the average change that occurred across all participants. The denominator is the standard error of those changes, calculated using the standard deviation of the differences, SD, divided by the square root of the sample size, n. If the average change increases, your t-value gets larger, showing a stronger effect. If you test more participants, n increases, which shrinks the denominator and makes your final result more statistically significant. Let us see the paired t-test in action with a clinical example. A doctor tests a new drug to lower blood pressure on 4 patients, measuring them before and 1 hour after giving the drug. Because we are measuring the exact same 4 patients twice, our first step is to calculate the difference for each individual. We subtract the after score from the before score. The blood pressure dropped by 10, 5, 15, and 5 points, respectively. We have transformed 2 sets of data into a single set of 4 different scores. Adding these up and dividing by 4 gives us a mean difference, d bar, of 8.75 points. Now we take our mean difference and plug it into the paired t-test formula. We also calculate the standard deviation of our 4 different scores, which comes out to approximately 4.787. This tells us how much the individual responses varied around the average drop. We divide this standard deviation by the square root of our sample size, which is exactly 2. Finally, Dividing 8.75 by 2.3935 gives us a t-statistic of approximately 3.65. This is a very large value. The signal is much stronger than the noise, so the doctor can confidently conclude the drug is highly effective, even with only 4 patients. To visualize why the paired test is so effective, look at this before and after diagram. The vertical line on the left represents the starting blood pressure for each patient, and the line on the right is their blood pressure after treatment. Notice how each patient starts at a completely different baseline height. If we just looked at group averages, those starting differences would create massive background noise. But the paired test only looks at the downward sloping lines connecting each individual. By analyzing the slope of these changes, it completely removes the background noise of individual differences, making it an incredibly sensitive test. We have covered a lot of ground today, so let us summarize the key takeaways. First, remember that t-tests are your mathematical detectives, comparing group means against natural background noise to find true statistical significance. Second, use the unpaired t-test when you are comparing 2 completely independent groups, like a treatment group and a separate control group. Finally, use the paired t-test when your data points are linked, such as measuring the exact same individuals before and after a treatment. The paired test is incredibly powerful because it eliminates individual baseline noise. You now have the tools to confidently analyze both types of experimental designs.